Okay, good morning, ladies and gentlemen. Happy Friday. Welcome to our second remote week question. So I had a nice list given out this morning by a couple students. So we're going to go through those. I'll try to go through them pretty quickly. But if you had a specific question, you can just skip around until you find that specific one. So I'm going to have a couple different things already added in. Some of them I have the solutions posted, and I'll just talk about them. But let's dive right in. So this is for section 4.1, question 24. If f of x is equal to e to the power of x squared, what is the equation of the tangent line at x equals 1? So I'm going to need a couple of things here. Basically, whenever you think of this equation of the tangent line, if we have some f of x looking like this, at x equals 1, the tangent line is right here. So I need two things. I need a slope and I need that y value. So to find the slope, slope is equal to f prime at that value. So we're evaluating our derivative at x equals 1. So I like to actually split this up, so I real quickly find f prime of x. So in this case, I have an exponential function. So if you remember, this was I leave the function alone, and then if it was just e to the x, it would just be e to the x, but in this case I have x squared. So I have a chain rule here, so I'm going to multiply it by 2x. So my f prime of x is going to be equal to, let me just clean this up, 2x e to the x squared. And then I want to evaluate at x equals 1, so f prime of 1, I'm just going to replace anytime I see an x, so it's going to be 2 times 1 times e 1 squared. This cleans up a little bit, so the 2 times 1 just becomes 2. E to the 1 squared is going to be just e to the 1, so I can say this is equal to 2e. So this here is my slope. My slope is equal to 2e of my tangent line. So if this was my tangent line here, this has an m of 2e. The other thing I need to find a y value. So whenever you're thinking of an equation of a tangent line, we're given an x value, we need a slope and a y value because our line's going to be straight, or it's going to be a straight line. So if you want to put it into slope-intercept form or whichever form you choose, you want it to have, you need a y value and an x value. So let's take a look at this. So I'm going to evaluate f at 1 because this is going to give me my y value. So plugging this in here, this is my original function, so it's going to be e to the 1 squared. Well, that's easy. That's just e to the 1, which I'll say is e. So I have the point 1 comma e with a slope of this. So if we remember our point slope form, it's going to be 1 minus our y value. So y minus e equals 2e x minus 1, and we should be done here. This is really quick, so you could put it into slope-intercept form, but you don't have to. This is why this point slope form is so good. All right, next question, number 26. If f of x is the natural log of x squared on the interval 1 less than x less than e on this interval when the average rate of change equals the instantaneous rate of change, or sorry, when will the average rate of change equal the instantaneous rate of change? So for whenever you see the average rate of change, this was kind of a common mistake in our most recent test. This is talking about a secant line. When it's talking about instantaneous, this is f prime of c. You're evaluating the slope at a specific point. And the mean value theorem basically says if I have some function and I have some interval here and I'm connecting the two, I'm going to find a point with this slope here. So I'm going to be able to find, it's going to be at least one point over here with the same slope. In this case, I have a couple, but you'll find at least one that has that same average slope. So first up, let's think about how we're going to solve this. This is an open interval, so if it was like this, it'd be a little bit easy, but again, this is continuous, so I'm going to take the endpoints and just try them out. So I'm going to take f of 1 equals the natural log of x squared equals, or sorry, this would be 1 squared equals, well, natural log here, 1 squared is just 1, so it's going to be the natural log of 1, which is equal to 0. And then f of e is equal to the natural log of e squared. Our log rules, if you have an exponent here, you pull the number out in front, so it's 2 ln of e. ln of e is just 1, so this is going to give me a value of 2. I should have technically pulled the 2 out in front, but natural log of 1 is equal to 0, so it really didn't matter. So in this case, I got my 2 points. And remember, for the secant line, in this case, it would be f of e minus f of 1 over e minus 1. It just matters that we line these up. So this is going to give me, well, if this is 2 and this is 0, I'm just going to have 2 on the top over e minus 1. Now, next up, so this is my average slope. This is my secant line. It has a slope of 2 over e minus 1. And what the mean value theorem says is that I should be able to find it. So what I need to do is I have to set my derivative equal to this. So f prime of x is equal to, well, f of x is equal to the natural log of x squared. So if we remember, this becomes 1 over x squared, so it turns into 1 over times chain rule 2x. So simplifying this down, I'm going to end up with 2 over x. Not bad. All right, so now I need to say, okay, well, I need to find a point where 2x equals 2 over e minus 1. So just to kind of show what I did here, I went f prime of x equals the slope of my secant line. So from here, well, x, you see we kind of have like an equivalent fraction here. This part here should just be the same as this part here, so I'll say x is equal to e minus 1. Done. Boom. Okay, next one. So this is what they were wanting here. So at what point on this interval is this the case? And we can see that it is on this interval right here. So we are good to go. All right, next up, we have L'Hopital's rule question. We have a limit as x goes to infinity of e to the 2x over 2x squared. So with this one, do we really have to use? Well, let's give it a try. We've talked about infinite limits before, and we see that this goes to infinity and this goes to infinity, but we can probably maybe see that this is bigger over big. So we've talked about this before going to infinity, but let's see if L'Hopital's rule helps us out at all with this. So I have e to the 2x on top, so e to the 2x over 2x squared on the bottom. So remember, L'Hopital's rule works if we have like a 0 over 0 or we have an infinity over infinity kind of scenario. And we can use this to solve the limit. Keep in mind, this is not the quotient rule. I take the derivative of the top divided by the derivative of the bottom. So derivative of the top would be, well, this is easy, e to the 2x, and then 2 to the x, or 2x, I take the derivative of the inside, so it's going to be a 2. I'll bring that out in front in just a moment. And then this is just a regular power rule, so I bring the 2 out, so it's going to be 4x. All right, so then I evaluate this at infinity, so I would have, let's clean this up, I can cancel that out, so I have e to the 2x over x. And if I want to evaluate this at infinity, well, you see I still have this infinity over infinity. So one of the things that they said was, do it again, because we're basically saying that, hey, what's the limit as this approaches infinity now? Well, I still have this problem, so I'm going to do it one more time. So again, I take the derivative. Okay, this one's going to be boring. I'm going to have e to the 2x times 2. So it does the same thing because we keep that part. We just happen to cancel that bottom part out, and then this becomes 1. All right, so now this, if I plug this in, I have e to the 2 infinity times 2 over 1. Well, this is very easy to see that we're going to infinity. So if we want to show it using L'Hopital's rule, remember we can use L'Hopital's rule multiple times. We can kind of stack it up. So we're sort of saying like, hey, we're plugging in a here, like we're doing a direct substitution, but if this gives you a thing, f prime of a and g prime of a are just different functions. So really we can just do L'Hopital's rule again and see what we get, just kind of treating them as their brand new functions. So we take another derivative and we keep going until it results in some sort of easy to find out solution. So hopefully that makes sense. So in this case, we're showing it goes to infinity, it blows up. This is sort of an easy one that you can see just by looking at it, by just remembering that an exponential function like e to the 2x is going to grow way, way, way faster than x squared ever could. All right. Next up, we're jumping into Chapter 5. So that was all the questions I had for Chapter 4. Chapter 5, all about curve sketching. This is one of my favorite sections because a lot of it involves, if you can remember the shape of the graph, you have a lot of things that can make your life a little bit easier. So for this question here, we're finding the absolute maximum and minimum functions on the given interval. So when you have a given interval, and you usually will, you have to first up check endpoints as well as f prime of x equals 0 or does not exist. So those are kind of your conditions to finding local extrema, maximum minimums. So checking the endpoints to figure out where we are. But let's talk about what this function looks like. This here is just really a sine of x plus a constant inside. So if I think about for a second, we're going from 0 to 7 pi by 4. So I'm going to have, pi. I'm going to have 2 pi over here. 7 pi by 4 is like over here. It's pi and 3/4. So if I think about the function, just if I start with f of x equals sine x, well, sine x starts at 0. Let me do the in between pi by 2, 3 pi by 2. If we remember, sine of x comes up, and then once it reaches pi, it goes back down to 0. This is a 1. This is a minus 1. So then 3 pi by 2, it reaches its maximum, and then it comes back up to 0 at 2 pi. So we basically have one full cycle of our sine function. But if I have this, imagine plugging in a 0 here, I'm going to end up with pi by 4. Well, pi by 4 is here. So I have this value, but it's over here. And then when I get to pi by 4, if I go pi by 4 plus pi by 4, I'm really at pi by 2. So my function is going to be at a maximum. So all this plus pi by 4 ends up doing is shifting my function over my pi by 4. So it is exactly the same. So our goal here is to think about our extrema. So if we're on this interval, so right here is where we end, right here is where we start, I can kind of look at the values that they're going to be. I'm basically evaluating at these different points. So in their answer, they were evaluating them, but really we're trying to think about, like, if it's a sine function, when is sine at its maximum minimum point? Well, normally it's when it's pi by 2, so what do we have to make this pi by 2? Well, if I want this to be pi by 2, I make x pi by 4. So this is where they get the x equals pi by 4, and they just plug in the value 1. Same thing for 5 pi by 4. Well, it would normally be 3 pi over 2, but it reaches it a little bit early. It reaches it here, so this would be 6 pi by 4, so they reach it at 5 pi by 4. So this is x equals 5 pi by 4. So this would give you your absolute minimum of -1. So this one involved a little bit of just understanding sort of the shape of the graph and what this pi by 4 does as a transformation. You can also kind of see that it's really, if we imagine it, this is asking about, what is the interval of sine x if our interval was pi by 4 to 2 pi. If I really look at the graph, that's what I'm looking at here, where it doesn't quite reach up, or where I'm starting at pi by 4, like I'm starting at this value here, and it ends at this value here. So I'm kind of taking all my values and shifting them over. So yeah, if you were a little bit confused, that's kind of the shortcut that I would have. But you can always also just show these and plug in values. Again, you're plugging in your endpoints, and then you're trying to figure out when the absolute max and min are. So for these ones, you kind of have to have some idea of when sine or when cos or when one of your trig functions reaches its top value. So hopefully that's a little bit clear. All right, for this one, I have their answer. They have a number of different ways. I like their solution. I'll show you a slightly different way. So we want to, again, find this absolute maximum and minimum, except our function is g of x equals x e to the 2x, and then we have on the interval -1 and 1. So again, I am thinking about g of -1, and I'm thinking about g of 1. And then I want g prime of x to equal 0 on the interval x is greater than or equal to -1, less than or equal to 1, or undefined. So this is what they ended up doing. So this here is a product rule. So they go through and they figure out this is the answer key in online. So they get this, they set it equal to 0, and then what their trick is, you have e to the 2x plus 2x e to the 2x. So when you see a case like this, it's really hard how you can equate it to 0. And it actually becomes really hard because this is never equal to 0. Hopefully you can see why. So what they did was that they pulled this value out. So then this side here is never equal to 0. So all they have to worry about is this part here. So this is where they get their minimum here. X is equal to -1/2. So they plug in endpoint, endpoint, and middle point, or the one value where our slope is 0. It's on our interval, so we can check it. So then they find the 3 values here, plug them into the original function, and you get your absolute max and absolute min. Another way you can do it, I have the pictures here because unfortunately I can't really pull it up, is if you have access to a calculator, I don't know if this is necessarily faster, but if you have a big nasty equation or something that's like not really derivable, like it becomes a huge mess, you can always plug this in. So if you go to if you go to y equals, and then you pull this up and you actually have the y1 equals x e to the 2x, and then you graph it, well, I've set my window here, so this is -2 and this is +2. Once you plug it in, you'll see that it gets really small, but I'm also doing it on my interval. I'm doing it between -1 and 1. So if I take a look at this, I see that I have sort of a value here, and then it comes all the way up. So what I do here is I go to my trace. So this is trace, and I just plug in my endpoint here, my value here for my 2 endpoints, and it'll give me the number here. So I could go -0.135. For over here, I could put 7.389. Now these numbers here, when you equate them, are identically equal to the functions that they give you here. And it's very easy to see that this is an absolute max. This one here, it's a little bit hard to see, but you can see that the line, if I kind of highlight it here, goes down and then up. So it doesn't look like a max or min in this case. So my last one, when I see the graph, it dips down below. This here is I'm doing a calculation. So I'm doing second function trace, and then I'm looking for a minimum. Now I plug this in, I put the left bound somewhere around here, the right bound somewhere around here, and then I guessed, somewhere in the middle. It gives you a rough approximation, so it's -0.5000000001, and that gives me this value here, which if I plug it in is exactly equal to this -1/2 e. So you'll get the same value. This case, they round up the last one just a little bit. Not sure why. Maybe my guess was a little bit off. Maybe my left and right bounds were a little bit too wide. But you can see that this is another way that you can do it. and that these values are identically equivalent to solving it algebraically. This one was probably one of the ones that you didn't need to solve. Like, you can actually do this without a calculator at all. And it's probably a little bit faster, but if you're just worried if it's a really messy equation, you can always do this, especially if it says that it's a calculator question. And then just using the idea that, like, hey, my interval is kind of my graph, I'm only looking at this point here, so I'm going to check this point here, and then visually look for any sort of max or mins or where the slope is 0. So I'm looking right there. So that's what I was doing here. That's what I'm showing you. Unfortunately, I can't actually show you me pushing the buttons because my capture software doesn't allow it for whatever reason. Alrighty. This is 5.2, so first derivative test. A particle moves along the x-axis with the position function given below. Find the velocity and use a sine chart to describe the motion of the particle. So we want e to the cos x. So first up, we're looking for velocity, so we need g prime of x. This is the rate of change. So remember, this is e, leave it alone, cos x, and then minus sine x. And on the interval 0 to pi. So for this question, let me just rearrange it. G prime of x equals negative sine x e cosine x. Now, important thing, we're looking for critical points here, so we're looking for where the slope is 0 or undefined. Keep in mind when this is equal to 0, so if cos x equals 0, then e to the cos x will equal 1. So this is one of the tricky points here with our exponential functions, is that they don't ever equal 0. They will as they go to negative infinity, but cos x goes between -1 and 1. So really, if I want to set this equal to 0, so like 0 equals negative sine x e to the cosine x, I'm really only looking at when negative sine x is equal to 0. And on the interval 0 to 2 pi, this is going to be 0, pi, and 2 pi. So when I make a chart, I'm thinking about in between those. So I have 0 to pi. I have 0 to 2 pi. I guess I only have 2. So at these values, my slope is 0. But I don't have an interval on this side. I don't have an interval on this side. So really, I'm looking at what happens in between those 2 points here. If it just so happens in this case that my endpoints match up really nicely with my values here. Now, if we want to test, we want to pick easy values. So I'm thinking about when this will become the easiest possible. Now, cos x equals 0 when I have the opposite, so pi by 2. So I'm going to test in between 0 and pi, so pi by 2. For here, I'm going to test in between, sorry, this should be pi and 2 pi. I'm going to test at 3 pi by 2. So I have g prime of pi by 2. So I have minus sine of pi by 2, and then e cosine of pi by 2. Well, this here, if cos of pi by 2 is equal to 0, this just goes to 1, and then sine of pi by 2 is negative or positive 1, so this is equal to -1. So I'm looking at the sign, it is negative. And then from here, testing 3 pi by 2, so again, I can plug this in, so I have g prime of 3 pi by 2. So I'm going to have minus sine, and maybe you can already see what's happening here. Give myself a bit more room. E cosine 3 pi by 2. And again, you're only looking for the sine, so again, pick values that make this as easy as possible. Sorry, I'll make that nice and big for us. This here goes to 1 again, and then, so really this part cancels out. 3 pi by 2 goes to -1, So I have a negative, -1, so it's going to come equals +1. So my sign here, positive. So if I want to describe the motion of the particle, I could say from 0 to pi seconds, particle is moving left, stops at pi, so I'll say x equals pi, and changes direction before stopping at x equals 2 pi. And I can also say starts moving at x equals 0. So it wasn't moving at x equals 0, so it starts moving in the negative direction, eventually stops, and then it turns around at x equals pi and starts moving in the positive direction. So again, I'm using that first derivative test to check when it's 0 to find my critical points, and then I'm testing in between them to check the sign to see which way my rate of change is pointing. All right, I think this is the last one. We're going to keep this to like a 30-minute video. So given the f of x, sketch the appropriate graph of f prime of x. Now this one they like to put in nice and tricky because it has, so in the back of my mind I'm going to put f of x here, and I'm going to try to draw this on the same graph, f prime of x. So they make it as tricky by adding in a little discontinuity, but first up, I'm going to check when is my slope 0, and then I've got this little discontinuity, so I can imagine it's going to jump right here. You might also be able to see that it's a positive slope over here, but let's start with the 0. So at -2, it's equal to 0. So I'm finding any point where the slope is 0, and I am placing a dot on the 0 line here. Alrighty. So if I take a look, it's a little bit positive, or it's more positive here, less positive, and then it drops to 0. So my graph is maybe doing something like, if I have an open function, it's coming down like this, or it might be coming down like this. Not sure. All I know is it's dropping down to 0, and then I have a little negative, I have a little more negative, a little more negative, a little less negative, a little less negative, and then 0. So this is doing something, probably, I'd have to do that second derivative test that we're familiar with, but it's going down, and then right around here, that's our sort of point of inflection that our 5.3 gets to, and then it starts coming back up. So I'm expecting it's going to start changing direction and head back up here. And then I see that it's a little bit positive, a little bit positive, a little bit more positive, really positive. So in between here and here, it's going to be going up and up and up and up and up. Don't know how high it reaches, doesn't really matter. And then here, it's closed interval, so I'm going to close this. And then if I take a look at this last line, now this is negative, but it's a straight line, so I can actually calculate the exact slope. So it goes down 1 over 2. So my slope would be negative rise over run, -1/2. So right here, I'm going to put an open interval, because up here it's defined, down here it's not. And between these, it is a straight line going this way. There is no change in velocity between those points. It's not getting faster and faster. It's not getting slower and slower. It's moving at a constant rate. So we are done. Now, again, we're going for approximate shape. So these endpoints, the slopes aren't going to be exact, but I should have an idea that it's changing direction and heading back towards 0. You absolutely need to get the zeros right. This here, because it's a straight line, I can absolutely calculate the slope, no problem. So it's -1/2, so I should be able to put in a horizontal line here. And knowing that, hey, when my line has, or when my f of x has this jump discontinuity, and I go from a big positive slope to some type of negative slope, I should be expecting to jump. It never hits 0, so I'm going to be expecting that my blue line, my f prime of x, will also jump simultaneously. All right, that brings us to about 29 minutes, 30 seconds, so that's all I have for you today. Thanks so much for bringing these questions up. Have a good one. Take care, stay safe, have a good one. I'll see you all on Monday. Bye.